All right, let's work practice problem 13 on page 129 because that gives people, it's a confusing problem to do. Let's take a look at it here. Zoom in. It says, use the results from the first example problem to answer these questions about a scale in an elevator on Earth. What force would the scale exert when? And it gives you these different things, and we'll set up that problem right now. So let's write out what's given. And so it's an elevator problem, just like the starter was today. Oops, not a very good elevator. And here's our person. Here's Gumby standing in the elevator. Here's the bathroom scale. Now, really all you need to know from the example problem is what the person's mass is. And it says the person's mass is 75 kilograms. Okay, so there's our mass. And what we're trying to find is the force of the scale. Now, the force of the scale on the person is really the normal force between the feet of that person and the scale. So, what we really want to find is the normal force. But if you want to call it F sub S for scale, and I think I saw some of you doing that today, that's fine. Call it F sub S or normal force, either way. Now, but what we want to do is we want to find it when, for part A, it says the elevator moves up at a constant speed. So the velocity is up, but if the velocity is constant, what's true about the acceleration? It's 0. And then for part B, it slows at 2 meters per second squared while moving upward. So the velocity is upward, but it's slowing down. What does that mean is true about the direction of the acceleration? It's negative, it's down. If the velocity is up and we're slowing down, that means the direction of the acceleration is downwards. And so we want to accelerate down at 2 meters per second squared. And the way we say down is negative 2.0 meters per second squared. And then for part C, it speeds up at 2 meters per second squared while moving downward. So here, the velocity is downwards, and we're speeding up. Now, if we're moving downward while speeding up, what's the direction of the acceleration? It's negative as well. Let me make sure I read that correctly. It speeds up at 2 meters per second squared while moving downward. So it's moving downward, it's speeding up, so that means the acceleration is also negative. Is that the way you guys did it? Is that okay? And then part D, it asks, it moves downward at constant speed. So here the velocity is downward, but the acceleration equals 0. And then part E, it says it slows to a stop at a constant magnitude of acceleration. So it stops, so you have some delta V where the final velocity is 0 and the acceleration equals a constant, and they want to know what's the normal force in that situation. Okay, so setting up this do and give and find is kind of a pain in the neck for this problem. Let's solve it. Now, what I'm going to do is draw one free body diagram that we're going to use for the whole problem. So here's our person in the elevator. And let's draw the forces acting on the person. So by the way, this was step 1 of our procedure. Step 2, draw the free body diagram. We've got the gravity, which I'm just going to call mg. And the force, the normal force pushing up on them by the scale. pushing up. Okay, now, then we're going to sum the forces in the y direction. Let's say that this is positive y is equal to MA in the y direction. What are the forces in the y direction? Well, we've got the normal force minus mg, because it's down, equals MA. Now, we're always trying to find the normal force, so let's solve this for the normal force. The normal force is equal to, let's add mg to both sides, so it's going to be mg, it's going to be our weight plus our net force. See what I did going from here to here? I just added this to both sides. I added mg to both sides. Well, now I'm ready to do the rest of it for each part. For part A, the normal force when the acceleration is equal to 0. So this is equal to 0. So the normal force is just going to be equal to the weight, which is 75 kilograms times 9.8 newtons of force for every kilogram of mass. And my answer is, what was that answer? 735 newtons. Okay. Now for part B, it's the normal force is equal to the weight, which I already know mg is now 735 newtons, minus, plus ma, but a is negative 2. So this is going to be 75 kilograms times negative 2.0 meters per second squared. So that's minus 150. And what do we get for the normal force there? So what is 735 minus 150? Well, it's 635. What is it? 585? 585 newtons. Now notice something here. Notice what's happening. You're going up in an elevator, but you're slowing to a stop. Isn't that when you feel lighter? Don't you jump in the elevator when that happens? I always jump in elevators. All right, so you feel lighter. Now, you aren't lighter, but you feel lighter because that normal force beneath your feet is less than your weight. In part C, notice that part C is just the same. The normal force is equal to 735 newtons plus 75 kilograms, negative 2.0 meters per second squared. I'm sorry? Oh, 735, thank you. Because you're going down, but your acceleration is also down. You're starting to, the elevator's starting to move down faster and faster. You also feel like when you're at the top floor and the elevator starts going down, you feel a little bit lighter. That's because the acceleration is down. So you don't need as much normal force. You need a net force that's downwards. So your normal force will be less than your weight so that you have a net force that's downward. And this is just going to be the same. And for part D, the normal force is equal to your weight plus, now it's just MA again, but your A is 0 here, so it's just going to be 735 newtons. That is, you're going to feel like your normal weight. Now for part E, it says, part E is kind of silly. It says it slows to a stop at a constant magnitude of acceleration. What do you need to know? Well, you know you're going to weigh, you're going to feel heavier. The normal force is going to be greater than your weight. But you don't know how much greater than your weight because they didn't give you enough information. So I would say, if I were to answer that, I would say, well, the normal force is going to be greater than 735 newtons, but I don't know how much greater. Right, remember when you're going down, the elevator comes to a stop, you feel a little bit heavier per second? Okay, so you're going to feel a little bit heavier than your weight, which in this case is 735 newtons, but you don't know how much heavier. It's not enough information. Not enough information. And that is the end of that long, tedious problem. Let's stop a little bit so you can see the whole thing. Okay? Any questions?